You need to give a permission to record.
Sure, please go ahead.
Berivan, can you hear me?
Yes.
Not you, dear professor.
Okay.
Berivan Hanım will give a permission to record your presentation. Then we will be ready.
Yeah, I'm giving you the permission to record.
Okay, now, okay, I got the permission. Okay.
Before the Suryanara, I would like to hi everybody.
Yes, I'm ready.
Hi Surya, how are you?
Fine, how are you doing?
Thank you, I am very well. Now I saw you, I am very happy. Thank you. You can.
Can I start now?
Yes, please, please.
Okay. Thank you so much, Professor Gokhan. I would like to thank the organizers for giving me this opportunity to present this keynote talk. And then I would like to talk about mechanical alloying of nanocrystalline materials and nanocomposites. The program lists 4 different topics. These were the possible topics I suggested, but then Professor Hakan Etes said he is going to combine everything. I said, fine. So I'm going to talk about all the aspects that were listed in the program, but I chose another title so that it will cover all aspects of this particular presentation on mechanical alloying of nanocrystalline materials and nanocomposites. So the outline of my presentation would be, I'll briefly introduce the topic and then talk about the developments in mechanical alloying, because the first part says over 50 years of mechanical alloying. And then I will talk about nanocrystalline materials in general, talking about the nano steels, and I would choose paralytic steels, cementite, and austenitic stainless steels to talk about this nanocrystalline aspect of steels. Then I'll go into the nanocomposites. And in the nanocomposites, I would like to specifically talk about 3 different systems. One is aluminum alumina. The other is titanium aluminide, titanium silicide composites. And then the third one will be aluminum metallic glass composites. The last topic listed in the program was the pathways in phase selection that I will cover in developments in mechanical alloying itself. Now, the first part will be basically the developments in mechanical alloying. And I'm sure most of the people attending this conference know what mechanical alloying is. But I would like to define mechanical alloying as a powder processing technique that involves repeated cold welding, fracturing, and rewelding of powder particles in a high energy ball mill. That means basically we use a high energy ball mill, and when we put the powders and the grinding media together, the repeated operations of cold welding, fracturing, and rewelding eventually forms an alloy. And because this is done under a mechanical force, this is called mechanical alloying. The potential of this technique of mechanical alloying, from now onwards, I would like to abbreviate this as MA, mechanical alloying. You can synthesize a variety of alloys, and all these synthesis does take place at very low temperatures, and in fact most of the time it takes place at room temperature, whereas traditional alloying requires melting, which requires very high temperatures, and no requirement here. You can also choose what constitution, that means what type of phases do you want? Do you want solid solutions, metallic glasses, or intermetallics, quasi-crystalline, nanocrystalline? You can choose. That's where the pathways to phase selection also comes in. Sometimes because of the difficulty in melting and alloying together in the liquid state even, those difficulty to alloy metals also can be combined using MA. You can allow chemical reactions to take place. This is a very big aspect of mechanical alloying. And then the most important thing for our applications now is nanostructures and nanocomposites. And there are some specific advantages which I will touch upon when I go to the actual nanocomposites sections. The most important developments, there are many, but the most important developments that took place in the area of mechanical alloying are the technique started in 1966. That means a little less than 60 years ago. And this was used mostly to produce oxide dispersion strengthened nickel-based superalloys. Then it was extended to iron-based superalloys and then aluminum alloys. Like that, it slowly diversified to different areas. But originally, this was developed in 1966 for ODS superalloys, especially for high temperature aerospace applications. But then in 1981, a Russian scientist showed that intermetallic compounds, if you subject them to mechanical alloying, they get amorphous. This was interesting. In 1982, the ordered intermetallics under the influence of mechanical alloying were shown to be disordered, because disordering also has certain advantages. In 1983, instead of intermetallics, one could use blended elemental powders, and those mixtures can also become amorphous. This was shown in 1983. This was done by Carl Koch. And then in 1989, the displacement reactions, that means where an oxide can be combined with a reduction metal, and then pure metals can be produced. This is what we call a displacement reaction. This was shown in 1989. And then same year, the quasi-crystalline phases, where the so-called forbidden symmetry, you can have 5-fold symmetry, 7-fold symmetry, 12-fold symmetry, all those so-called forbidden symmetries could be observed in these quasi-crystalline phases. 1991, for the first time, it was shown that mechanical alloying can produce nanostructured powders, powders with nanometer size grains. And in 1996, the so-called bulk metallic glasses, which were traditionally produced by solidification methods, have been produced using mechanical alloying. Of course, it is not bulk in the real sense of the word. You produce the powders, those powders can be consolidated to any section size, and that's what we call the bulk metallic glasses. But subsequently, a lot of effort has been going on to understand the science of mechanical alloying and also develop new applications for this particular interesting technique. There are many applications already existing, but there are more and more coming up in the years to come. Now, another technique which was very popular around the same time was called RSP. It's called Rapid Solidification Processing, RSP, and mechanical alloying and RSP, both of them are non-equilibrium processing methods. That means by subjecting the materials to rapid solidification processing or mechanical alloying, you produce a variety of metastable phases, and you can change the microstructural conditions. That means instead of crystalline, you can make it amorphous, you can make it nanocrystalline, you can make it quasi-crystalline, or many other possibilities of combinations exist. And therefore, the attributes of both RSP and MA are very similar. But the important difference is RSP, rapid solidification processing, requires that the alloy is melted, because you have to melt it and then solidify it very rapidly. That's why it is called rapid solidification processing. If solidification is involved, that means the phase diagrams will determine what type of phases are produced in these materials. Although metastable phases are produced, which are not part of the phase diagrams, but phase diagram still imposes some restrictions on the type of phases that could be produced. On the other hand, mechanical alloying is a completely solid state processing method. That means the phase diagrams do not come into play. And that's the reason why virtually any type of alloy can be processed using the mechanical alloying methods. but there are some restrictions or limitations on how the alloys can be produced by rapid solidification processing methods. So there's an important difference. So now I'm going to talk about the pathways to phase selection, wherein we will first talk about solid solubility limits. As I said, both rapid solidification processing and mechanical alloying can increase the solid solubility levels and produce supersaturated solid solutions. What I'm trying to show here in this particular slide is choose a few alloy systems. There are many different type of alloy systems that have been investigated both by rapid solidification and mechanical alloying, but I've chosen only a few wherein I would like to show the maximum equilibrium solid solubility in this particular column. The extended solubility limit achieved by rapid solidification processing and the extended solubility limit achieved by the mechanical alloying technique here. You can see in some cases, instead of 14% maximum solubility of copper in silver, you can go to 100%. That means silver and copper can be made an isomorphous system. In fact, if you look at the Hume-Rodri rules for solid solution formation, silver copper are supposed to be forming the isomorphous system, but it forms a eutectic system. And if somebody was asking, why is it a eutectic? Oh, it's an exception. That's how people use it to have a hand waving argument. But by non-equilibrium methods, you're able to increase the solubility of copper in silver from 14 to 100%, both the techniques. Whereas in other systems, you do not expect 100% solid solubility, but only a small increase. But the difference between RSP and MA is by mechanical alloying, you're able to increase the solubility to a much higher level than what is possible by RSP methods. You can see, for example, 9%, 18%, 2%, 36%, 4.5%, 50%, 6%, 37.5%, like that. But I also should confess here, but there are certain cases where you are not able to increase the solubility either by RSP or MA to a large extent. To a limited extent, yes, but not to a very large extent like this. So I've chosen a few typical examples, but not everything. Now, how do we understand the formation of these supersaturated solid solutions here? If you look at the silver copper system, copper and silver, these are the lattice parameter values obtained by mechanical alloying, and these are the values obtained by rapid solidification. You can see they form continuous series of solid solutions, whether it's by RSP or by MA, there does not appear to be a significant difference between them. Both of them do have a slight positive deviation from the Weygard's law prediction of variation of lattice parameter with the solute content. Now, if you looked at any of the solid solution formation cases, Hume-Rodri had suggested that you can have solubilities limited by two different factors. One is the atomic radius and the other is electronegativity. Of course, valency also plays an important role and the electronegativity also plays, but let us look at only some of them. Now, if you plot the atomic radius on the y-axis against the solute content, now you would see that if you looked at the copper as the solvent, plus or minus 15% are the limits suggested by Hume-Rodri. This is plus 15% of the atomic size. This is minus 15% of the atomic size. The bars here represent the extended solubility limits of the different alloy systems. That means copper, silver, copper, aluminum, copper, cobalt, copper, chromium, copper, mercury, copper, antimony, like that. And the black points represent the atomic radius of these elements. For example, this is radius of nickel, this is radius of mercury, this is radius of cobalt, like that. What you would notice is that the maximum solid solubilities are obtained only when you are in this particular range. The moment you go outside this range, the values seem to be very limited. And that you can see very clearly here, here, here, here, like that, or here. But there are some exceptions, but we will not talk too much about it because we do not have enough time to talk about these right now. And then you can also have the nanocrystalline materials produced. Because of this, because you're producing crystalline phase, you can have nanocrystalline materials. Nanocrystalline materials means materials with a grain size of 100 nanometers or less. What you would notice is by mechanical alloying, it is always possible to produce a crystalline material with a nanometer grain size. So I'm listing here the FCC, BCC, and HCP type of systems. All these values are listed here. You can see the minimum grain size achieved is less than about 25 nanometers. But what I'm showing here is the minimum grain size plotted against the melting temperature of the element. And therefore, if you now look at this, with increasing melting temperature, the grain size produced decreases. That means if you have a very high melting point metal, it's possible to produce very fine grain sizes. If it's a relatively low melting point metal, the grain size is going to be large. And here, of course, we are talking about 1000 degrees Kelvin, but very low melting point metals is more difficult. And that's the reason why, if you want to determine what factors are responsible for determining the grain size, there are two things. One is defect creation. If you create more defects, it's possible to decrease the grain size. But recovery also takes place because of the heat effects, and therefore the grain size increases. The balance between the defect creation and the recovery will determine what the final grain size is. To put it very succinctly, the grain size decreases with increasing milling time, with increasing milling energy, with the increasing solute concentration, high ball to powder weight ratio, and with increasing melting point of the metal. So you can determine what are the more important factors for your investigation. Metallic glasses also are formed by this particular techniques, both RSP and MA. Just like in the solid solution cases, here also by mechanical alloying, you're able to increase the glass forming composition ranges. They are more than what is possible by rapid solidification processes. And is a very similar technique. Essentially, the MA seems to be more effective. The reason being the amount of departure you can achieve by mechanical alloying is more than what is possible by RSP methods. Now, these nanocrystalline materials sometimes become very difficult to consolidate, and this is the way you can think of a consolidation rate or the densification rate equation, where there are two very important things. One is the bulk diffusivity, and the second is the grain size. This represents the densification rate. So if D decreases, the densification rate increases, or if the diffusivity of either the volume or the grain boundary increase, this densification rate also increases. But in the case of nanocrystalline materials, the diffusivity is higher, the grain size is smaller. As a result of this combination, the densification or consolidation of nanocrystalline materials is very easy, and that is something which is an advantage for nanocrystalline materials. But the problem is, if you wanted to use the densification process, is not easy to get a material which is both dense and also at the same time fine grain. Fine grain means you need very low sintering temperatures. But low sintering temperatures means bonding is not going to be good. For this, you need high temperatures. That's where there is going to be a dilemma, and that's the reason why nanocrystalline materials are better in a way. To conclude this particular part of the lecture, the developments in mechanical alloying, as I said, they started in 1966 with the production of oxide dispersion superalloys. But by about 1986, it turned out that people tried to produce amorphous alloys, solid solutions, or the development of basic understanding. Why do these processes occur this way? How do you determine the type of phase that is produced? All the scientific basis for understanding the process of mechanical alloying started developing in 1986, but then it is still continuing. But then 1991, as I said, nanostructures were produced, and then this is continuing even now, and new applications also are being generated. Therefore, you would see that these two aspects are continuing, but the ODS alloys, there is not really much that is going on, and that's the reason why I did not put an arrow here. Okay, now the conclusion of this part is a simple and economic materials processing technique. You can determine what the phase you want and what the phase proportions by optimizing the process parameters. Powder contamination could be an issue, but that can be minimized or completely avoided at some cost. You can design, synthesize, and produce a variety of advanced materials using this technique of mechanical alloying. Now, I'm going to talk about the nanocrystalline materials. This is again something a lot of people know, probably everybody knows. A grain size of 1 to 100 nanometers will qualify a material to be called a nanomaterial. But this nanomaterial is not really very new. People talk about this so-called Lysergus cup, which is residing in the British Museum now. And this is a cup made with glass, basically. And this was done in around 4th century. And therefore, you can see, if you put a light outside this cup, that means in reflection, the glass color will be green. But if you put a light inside the cup, that means you look at the transmission, then it turns red. The reason appears to be that when you made these cups, there were very small gold particles, which are approximately 70 nanometers in size. And because of these small gold atoms, particles, the optical properties are different, both in reflection and in transmission. And you can also these cathedrals in most of the parts of the world. Again, this is again because of the nano-sized gold particles present in the glasses that were produced for these applications. But the most important thing is the nanostructured materials. The important point is very small grain size. If I look at this, it does not tell me anything about the nature of the material, except when I see the nature of the grain boundaries. The grain boundary atoms are many more. That means it's a nanocrystalline material. Whereas if it is a coarse-grained material, the number of atoms in the grain boundaries will be much less than what they are inside the grains. And this large volume fraction of atoms residing in the grain boundaries is the factor which will determine the interesting and very important properties of nanostructured materials. You can have new and improved properties and functionalities. Materials, if the grain size is less than 30 nanometers, they behave even completely differently, and therefore people feel that there is unlimited potential for applications of these nanomaterials. You can have all these property changes as a function of the grain size. If you take a nanocrystalline materials, You can increase the ductility and toughness, but at the same time, you can also increase strength and hardness. Typically, in a coarse grained material, if strength is high, ductility is low, but in a nanocrystalline materials, you can achieve both of them. Diffusivity is high, thermal conductivity is low, electrical resistivity is higher, magnetic properties are improved, coefficient of thermal expansion is higher, modulus of elasticity decreases. And because of this interesting combination, a lot of new applications are being developed. So with this as the background, I would like to talk about the nanostructured steels. And when we talk of the nanostructured steels, I wanted to focus on three different aspects. One is the so-called pearlitic steels, that means iron containing about 0.8 weight% carbon. The second is pure cementite, that means iron containing 6.67 weight% carbon. And the third one is the austenitic stainless steels, the so-called 18-8 stainless steels, that means iron with 18% chromium and typically 8% nickel. What we wanted to see was what will be the effect of nickel content on the formation of these austenitic stainless steels in this mechanical alloying process. So all these are now developed only during mechanical alloying, and my talk will talk only about mechanical alloying and not the others. These are the process parameters. We started with a specs mill, very low ball to powder ratio, but then we consolidated these materials using spark plasma sintering at relatively low temperature, 600 degrees C, just for 15 minutes, and using a relatively low pressure of 70 megapascals. But we were able to get complete densification. So if I now start with the iron 0.8 weight% carbon, you would notice that in the as milled condition, I have a few peaks representing carbon still, and then I have cementite, and I also have the ferrite. So I have the ferrite peaks, then after some time, after about 15 hours of milling, cementite starts forming. Or in other words, in the initial stages, only a solid solution is formed, and then intermetallic Fe3C starts forming afterwards. And if you increase the time to up to about 30%, this is the picture, but an enlarged picture shows very clearly that we have only alpha iron and Fe3C. And if you subject this powder milled for 30 hours to spark plasma sintering, as I indicated earlier, you can see the peaks are very, very sharp because there is an increase in grain size, and all the strain that was present in the milled powder is also released. Therefore, you can see very sharp peaks and very high intensity peaks, and therefore you will be able to easily identify the phases which turned out to be only alpha iron and Fe3C. This is what we expect even from the phase diagram of iron carbon. The grain size decreases continuously and reaches something like about 6 to 7 nanometers. And the strain in the powder increases. And these are the two reasons why the peaks in the previous plot, for example, are very broad. So all those are gone by spark plasma sintering. Now, if you look at the microstructure, in the SEM, this is the way the microstructure looks like. But if you go to the transmission electron microscopy studies, you would notice that you have, again, alpha iron, that means the ferrite, and cementite. But if you have a pearlitic type of composition, that means 0.8 weight% carbon, you normally expect to see the so-called lamellar structure, the eutectoid lamellar structure. You don't see them. You see essentially equiaxed, very fine. The micron marker is 0.2 micron. This is only about less than 50 nanometers, even after consolidation. Now, if you look at the microstructure, after annealing, that means it is subjected to spark plasma sintering and then anneal at 900 degrees for 1 hour, you still have the same phases although the proportions of the phases is slightly different, but essentially the same two phases continue even after annealing. Now you see the lamellar structure, the eutectoid lamellar structure, you can see it very clearly after annealing, because the very, very fine grain sizes would preclude the formation of these lamellar type of microstructure. And that's the reason why only after annealing, you can see very clearly, these are the TEM, transmission electron micrographs. These are the scanning electron micrographs. You can see the ferrite, cementite, ferrite, cementite, alternate lamellae, and then you have the diffraction pattern. And if you look at the dark field picture, the white portions here, the highlighted portions represent the ferrite portion, because this is taken from one of the ferrite reflections. So you can produce these things very uniformly by our technique. But this is a micrograph from one of the previous workers, wherein you can see large grains, small grains, grains of only ferrite. Like that, there are variation, or in other words, the uniform distribution of the two phases is not there, and therefore the properties also are not going to be uniform. But by our processing, by adjusting the process parameters, we're able to take care of all of these things. Then you can produce pure cementite also using the technique. Take iron, 6.67% carbon. You can see only cementite reflections in this particular case. And if you look at the TEM, you can see after SPS at 600 degrees, you can see equiaxial grain of cementite. And if you look at the diffraction pattern, you would see that only the cementite is there and no other phase is present in these materials. But after SPS, you anneal it also, again, like in the previous case, you can get very sharp peaks. And then because this is annealed at 900 degrees Celsius, some amount of alpha ferrite also has formed in this particular case. And if you look at the microstructure, again, you will see the distribution of grains, which are larger than in the previous case, but the diffraction pattern indicates ferrite and cementite, both of them present, but the amount of ferrite is relatively small in proportion. I can measure the hardness values, and when I measure the hardness values, if it is fully dense, the perlitic steel has a hardness of 638 Vickers. And if it is a cementite, 900 Vickers hardness number. By annealing and quenching, you can adjust the properties very easily. And if you look at the hardness indentation of the cementite, you can see all these cracks indicating that the material is relatively brittle. Now, if you now look at the austenitic stainless steels, as I said, typically you see 18 chromium and 8 nickel. But we wanted to study the effect of nickel content. And now if you look at the material milled for 30 hours, you can now see the 18-8, that means 18 chrome, 8 nickel. You can see both gamma and some alpha, that means the austenite phase plus some ferrite. Increase the nickel content to 12%, the amount of ferrite has decreased. You increase the nickel content to 20%, there is no ferrite present at all, pure austenite. Now, if we anneal this, obviously the patterns are going to be much more clear. And here again, you will see, even after annealing, you still have some ferrite in both 12 and 8% nickel, but 20% nickel, obviously, because there is no ferrite here, here also you do not see any ferrite present at all. So what we did was look at the electron microscopy results. You look at the grain size. This is 50 nanometers. This is obviously less than about 10 nanometers. And when you go to a higher resolution, you can find out what the actual the diffraction patterns are in different regions. And what you would notice is you will see the presence of both alpha and gamma, that means ferrite and austenite. And the same thing is in this particular case, in just one general area. But if you can choose any one particular area and use this microbeam electron diffraction or nanobeam electron diffraction, you'll be able to get a better picture. On the other hand, you go to 20% nickel, everywhere you will see only austenite. That means the X-ray diffraction results are confirmed using this particular type of technique also. So if you look at the constitution, now you will see 8%, 12%, 20%. The amount of alpha and gamma is different, and the amount of gamma is increasing after annealing, although ferrite is still continuing to be present. So I can plot some sort of a stability of the austenite. Typically, at 8% nickel, you expect it to be only austenite. But what we notice is we are able to increase the solubility region or the stability region of ferrite even almost up to 15%. If you go to 12 or 20%, only austenite, but from 8 to 15%, you can have both austenite and ferrite. So essentially, you're able to produce different types of steels and obtain interesting properties and microstructures. Now I would like to focus on nanocomposites. This is the last part of my presentation. Typically, when you have a particular reinforcement, that means in a composite, you have a matrix and a reinforcement. If you have a reinforcement, depending upon the size, the distance between two particles is going to be different. The larger the particle size, the larger is the spacing between particles. Typically, when you do a very traditional composite, you use this particular region where you can produce composites with a large volume fraction of the reinforcement, maybe 30% or 50%, like that. This is easy. But if you go to very small size reinforcement, 10 to the power of minus 2 of a micrometer, that means about 10 nanometers, 100 nanometers, in that range, you can see that typically you can put only 2 to 5% of the reinforcement. More than that is difficult to mix thoroughly. But our goal is, can we increase it? Can we push this to this level, maybe 30% or 50%, like that? So what we started with was the alumina system. The alumina particles are 50 nanometers. And we said, let's take 20%, 30%, or 50% by volume of alumina and see whether we can distribute it uniformly by mechanical alloying. And what we see is you can produce very uniform distribution of alumina in the aluminum matrix by increasing the milling time to approximately 20 to 24 hours. And is very uniform. And this is confirmed by EDS mapping technique. And I'm not going to show all those details here. But if you now consolidate those materials and then measure the properties, yield strength, compressive strength, elastic modulus, depending upon the particle size, whether it's 50 nanometers or 150 nanometers, 5% and 10% in this particular case, you can see the modulus increases with increasing volume fraction of the reinforcement, and the actual yield strength also increases and the compressive strength also increase. So obviously there is a significant improve in the properties. But what we would like to know is, how is the load bearing capacity of this particular material? So what we did was subject this material to neutron diffraction. And when we subject it to neutron diffraction, you can record the neutron diffraction pattern. And at the same time, you can also apply a load. So if you take any one particular peak, for example, like this, and follow what the position of this peak is, that means change in the interplanar spacing as a function of stress, the change in interplanar spacing can be converted into the strain in the material, and you also know what the actual stress is. You can get stress strain plot, and once you get a stress strain plot, you'll be able to determine the modulus of elasticity. And now you would see here, if I plot this stress strain curve, but for one, this is aluminum, the metal, and this is alumina, the reinforcement, you can now see beyond the macroscopic yield limit, there is a curvature change. And whereas here, there is a slight curvature in the opposite direction, indicating that the alumina is able to take up the more load, but still not show, excuse me, not show much of the deviation from the linearity. That means the stiffness of this particular material is going to be quite high. So that's what we are to consider. The second type of composite I would like to talk about is titanium aluminide containing 60 volume percent titanium silicide. This is a very high volume fraction of a reinforcement in a titanium aluminide. The reason we wanted to check this was titanium aluminide can be superplastically formed around 1300 degrees Celsius. But is it possible that we can reduce that temperature to lower values by having the nanocrystalline or ultra fine grain size? So we took mixtures of titanium 48.9 aluminum corresponding to this, titanium 37.5 atom percent silicon, but this is not exactly this. So we add extra silicon to produce this particular composition, which corresponds to 60 volume percent of the titanium silicide and 40 volume percent of the titanium aluminide. That means this is basically titanium silicide based composite containing titanium aluminide. So we mill the powder, we sieve the powder to different sizes. The coarse powder is dehydrogenated at 440 degrees and then subjected to heaping, hot isostatic pressing at 1050, 1100 and 1150 degrees Celsius and studied the microstructure. Now, if you look at this, the microstructure is very, very fine. And now you can see both the titanium silicide and titanium aluminide, both of them are present. Gamma titanium aluminide, you can see twinning present. So the presence of these twins will indicate that this is the titanium aluminide grains and the others are the titanium silicide grains. So it's like a very small grain size of both the matrix and the reinforcement, and both of them are uniformly distributed. This is the type of microstructure which is conducive to formation of superplasticity. So we measure the strength as a function of temperature. Obviously, with increasing temperature, the strength decreases, and this is for 60% silicide. It decreases even up to 1000 degrees Celsius. Now, you can do the stress strain test on this material at different strain rates and at different temperatures. 950 degrees, 10 to the power of minus 4, you would see is almost like elastic deformation only. But if you increase the strain rate, or sorry, if you decrease the strain rate to 10 to the power of minus 5, then you can observe elongation almost up to 150%. Even at 1000 degrees at higher strain rate, you can see almost like 100% elongation. This should be compared with what we normally see in a coarse grain material. For example, before testing, this is the type of microstructure, as I said, uniform distribution of the two phases and equiax. After deformation, after this superplastic testing, you can see the grain size is a little larger than here, but they're still equiaxed. That means the deformation is superplastic and not like elongation. And that's confirming that we are able to achieve superplasticity in this composite at a low temperature of 950 degrees at low strain rate Or if you go to 1000, even at a higher strain rate, you'll be able to achieve this. Conventional coarse-grained materials will be having only this deformation occurring like this at 1300 degrees Celsius, which is too high. Now, I wanted to talk about the last type of composite, which is very new, and that's the reason why I thought it's interesting to talk about it. So far, we talked about ceramic materials or intermetallics dispersed in a metallic matrix. But what will happen if I introduce a metallic glassy powder inside a metal? And so we took aluminum 70-75 powder, added 0, 2, 6, and 8 volume percent of the titanium, copper, nickel, aluminum glassy powder, mechanical alloyed it, and then cold pressing at room temperature and then hot extrusion. Then you have all these different techniques to characterize this material. So if you mill this powder, obviously there is going to be a deformation taking place on the surface of these metallic glassy powder particle. You can see these metallic glass powder particles, white particles here, and then the grayish area is aluminum 70-75. This is 10 hours. You increase to 15 hours, the deformed region, the amount is increasing, and then you go to 30 hours, 50 hours, like that, you'll be able to see the more uniform distribution of these, and then this is not almost very clear at all. But if you look at the TEM pictures, you would notice that there are all these metallic glass particles all around, and these with blue arrows represent the magnesium silicide, because this is hot extruded at a relatively high temperature, and therefore the magnesium silicide also has precipitated out along with the metallic glass particle. But the important point here is this nanoparticle reinforcement. You can see it is still amorphous. So they have a reinforcement. This is the alpha aluminum matrix, and the interface is there because of the small reaction that took place between the aluminum and the reinforcement. If you now look at the mechanical properties, you can see you can reach almost like a gigapascal strength, which is very high for an aluminum alloy. And of course, the amount of time for which you mill is important. If it's a very low timing, is not very high, but by 50 hours, because the grain size is going to be decreasing, you'll be able to get very high tensile strength. And now, if you look at the comparison of the present aluminum matrix composites with the other types of composites, and if you plot yield stress versus metallic glass volume fraction, you're able to get a very high yield strength, even at a low volume fraction. Obviously, if you increase the volume fraction, this is going to be somewhere here even. And therefore, we have achieved the goal of increasing the strength. But there is interesting phenomenon occurring in this. If you plot the compressive stress versus strain, true stress versus true strain curves, you can see there is going to be some sort of a reversal taking place. The black line here represents the pure 70-75 and is 2% and 6% of the metallic glass particles. This is at room temperature. But if you now come to 450 degrees Celsius, for example, the aluminum 70-75 is on the top. That means it has a higher strength than the composite. And that is something which is interesting. And if you plot the ultimate flow stress as a function of the volume fraction of the reinforcement, you can see at different temperatures, there is a reversal that is taking place. Or if you plot the stress as a function of temperature, there is a reversal taking place around 150 to 175 degrees Celsius. And this is interesting because a composite is weaker than a monolithic material at higher temperatures. So we looked at the possible reasons. Many different possible reasons are there. Thermal softening could be there, or damage accumulation could be there, or there may be large reinforcements or the medium-sized reinforcements. All these possibilities exist, but none of them seems to be present. But the more important thing, why we were able to get this particular situation is because the overaging of the matrix takes place because aluminum 7075 is a age hardenable alloy. Overaging takes place. The reason being there is a lot of difference between the coefficient of thermal expansion between the reinforcement and the matrix that causes stresses. Those stresses cause generation of dislocations. Those dislocations act as heterogeneous nucleation sites for the formation of a precipitate, and that accelerates the process, and that's why that's the responsible. So to conclude this nanocomposites area and in general, high volume fraction, as I said, up to 60% we were able to get it. The load sharing capability was determined using neutron diffraction studies. And then mechanical behavior is in general improved. Superplasticity is observed and very abnormal, where the matrix seems to be stronger than the composite is observed in some of these types of composites. So these are some of the references which you can think of. Most of these are my publications. In fact, all of these are my publications. I've done extensively in mechanical alloying bulk metallic glasses and two very important references in progress in material science. And I would like to thank you, Professor Gokin, and then we would like anybody interested in asking questions. I'll be happy to answer.
Okay. Thank you very much for your presentation, dear professor. It was very, very great and fruitful for me. And I believe that the audience also have good information because of your presentation. Some audience listening you in this room, maybe they have some questions. Do you, dear audience, do you have questions?
Professor Shalabani, I wanted to first of all express our gratitude. So thank you for the great presentation. My question is regarding the beginning of your presentation. You mentioned that the solubility increases in equilibrium. Can you elaborate on this issue? Is this perhaps because of a higher amount of defects in the metal, or perhaps disorder in the system? I'll be grateful for more elaboration in this regard. Thank you.
Professor Gokan, I think the voice is breaking. I'm not able to hear it very clearly. Will you be able to please repeat that question?
Same
Sure,
as me.
Professor. Is the voice coming all right now?
No, it's not very clear. There's a lot of disturbance in the background and the voice also is breaking.
I see. Perhaps I should write it in the chat and...
Yeah, now excuse me, now it's okay. Can you repeat the question?
Perfect. Yeah. My question is regarding the solid solubility of the non-equilibrium that you mentioned earlier. Is this perhaps because of the higher amount of defect in the atomic level, or perhaps more disorder in the system? I'd appreciate if you elaborate in this regard.
The distribution of the solute atoms inside the solvent is going to be, or is expected to be, on an atomic level, not on a gross level, but on an atomic level. But depending upon the time for which you mill, the distribution may or may not be uniform. And that's the reason why it becomes important that you do optimization where there is no more change in the grain size distribution and the distribution of the solute atoms. And once you have the so-called steady state condition, that means no more changes take place afterwards, then you can be sure that there is very uniform distribution even on an atomic level. But let me also warn you, the nature of the process, the nature of the mechanical alloying process is such that you will not be able to expect completely uniform distribution everywhere in the powder because it is a stochastic process. That means in some areas, there is going to be more deformation than in other areas. And therefore, there is some heterogeneity which is always possible present in a mechanical alloyed material.
Thank you very much, sir. It was an absolutely amazing presentation. Regarding the initial parts of your presentation, you had mentioned about the higher solid solubility and as a result of mechanical allowing. Is there any perhaps any reason that would be related to any atomic level phenomenon? Any further elaboration on the solid solubility as well? Thank you.
Okay, the answer is this. Solid solubility limits are higher in the mechanical alloyed condition than even in the rapidly solidified condition. The reason is like this. If you do mechanical alloying, you can calculate what is the energy that is put into the material. Or in other words, you can determine the departure from equilibrium. The larger the departure from equilibrium, the more highly unstable the material is, and therefore you can produce more non-equilibrium effects. And when you do the calculations, it turns out that the mechanical alloying is more energetic than rapid solidification processing. And that's the reason why you will be able to see higher solid solubility limits by mechanical alloying. And this is on an atomic level, essentially determined by the collisions between different types of atoms. The collision frequency is the one which is going to determine what type of phases are produced and what is the extent of deviation from the equilibrium condition.
Thank you very much, sir. An absolute eye-opener. Thank you.
Thank you.
Thank you.
Is there any question for this presentation? I think no, right? Thank you very much again, dear professor. I would like to thank you for our commission and Professor Hakan Ateş. He is also here. Maybe he would like to say something after me. Dear Professor Hakan Ateş.
Yeah, thank you very much, dear Gökhan. Thank you very much, Surya. I couldn't understand something. Thank you for this good presentation. Thank you for support us every time. I hope next time, I mean that probably next year, I will host you in Turkey. After your lecture, we will visit perfect places all together with Gökhan Küçüktürk.
Thank you so much, Professor Hakan.
Thank you.
Thank you. Yeah. Okay.
Shall we go on? What's next presentation?
Thank you, Professor Gökhan. And I would like to sign off now.
It was great to meet you.
Thank you so much. Bye.
Okay, thank you for everything, dear professor.
Bye.
Okay, now the next presentation will be given by keynote speaker, Professor Dr. Mehmet Türker. Are you there, Professor? Dear Professor?
I am here. I am here, Gökhan. In a few minutes, we will be ready. Okay.
Okay. We are waiting for you. You can share your screen.
Masa üstünde. Ha, o değil de masa üstünde arkada. Onu indir. Bir daha indir aşağı. Tamam, şurada ben açayım bakalım. Şu. Hemen şu. Şu. Şurada. Şimdi nasıl ediyor? Is it okay? Gökhan görebiliyor mu acaba?
Yes, we can see your screen now and presentation as well.
Okay.
When you are ready, you can start.
Can you see me, Gökhan?
Yes, we can hear well.
You can hear and you can see me, okay?
Yeah.
Oh, that's good.
Exactly,
That's good.
clear. Yeah.
Just a moment. Good afternoon, ladies and gentlemen, and good morning for USA. I will talk about aluminum foam reinforced with boron carbide and silicon carbide particles, production process, characterization, properties, and application. Actually, after nice presentation of Surya, it is really difficult to talk here. Okay. Briefly, I will give some information about metallic foam, properties and applications, production routes. I will not talk about casting. I will talk about powder metallurgy routes, conventional routes, metal foam filled tubes, sandwich foams, spherical foams, which is also called advanced foam morphology. And we have done some small experiment, and I will give some experimental procedure, experimental result, and maybe this is important, plus properties of metallic foams, and then I will finish my presentation with conclusion. Actually, recently, intensive studies on light alloys are continuing. Metallic foams, especially aluminum foams, are one of them. Metallic foams are ultralight cellular materials consisting of gaseous and solid phase together, which contain a porosity of 50 to 90 volume%. Metallic foams have been developed as a new engineering materials, particularly in space and defense industry, as well as automotive industry. These ultralight materials possess unique mechanical properties, such as high compression strength, stiffness, good damping, and high fire resistance properties, remarkable vibration attenuation, high impact energy absorption at low weight. Much attention is paid to control of the morphology of cell during the forming process of melt. Actually, there are lots of parameters that can be changed. These are forming temperature, that is important, alloying elements, forming duration, that's also one of the most important things. Another is the amount of reinforcing element. Now we will work on this today. The mechanical properties of metallic foams, particularly reinforced foams, are superior when compared to polymeric foam materials. High temperature resistance and their maintenance of structure at high temperature are two of their most important properties. Actually, there are two types of pore morphology, open and closed pore morphology. We are dealing with closed pore morphology. Some promising properties of metallic foams are low density. Actually, that makes this material popular. High compressive strength, that is also another important properties of metallic foam. High strength, high stiffness, high sound and heat insulation properties, remarkable vibration absorption, high impact energy absorption. Actually, because of these properties, we are working on this material as an armor material. Fire resistance also another important properties of metallic foams. Excellent properties make foam particularly attractive for automotive industry. Some leading automotive companies are working hard to use metallic foams in appropriate part of their wheels. Lifting and conveying system, transport, ships, and aerospace application, sound and heat barrier, internal armor plate sport. Actually, this is the new subject. I'm sure that we are one of the first scientists working on this subject. The study of metallic foams, particularly aluminum one, has become attractive to researchers interested in both scientific and industrial application more than a decade. Experimental studies have shown that almost all materials are turned into foam. Aluminum, zinc, tin, lead, iron, nickel, brass, and their alloys can be produced by powder metallurgy route. Nowadays, we are working with copper and even with gold. When we look at the powder metallurgy route, the production of aluminum foams via a powder metallurgy route is attractive due to the ability to produce near net shape components. This method involves mixing aluminum or aluminum alloy powder with a foaming agent. Generally, we are using titanium hydride, reinforcing elements, silicon carbide, boron carbide, aluminum oxide, etc., followed by compaction such as hot pressing, cold pressing, extrusion, or combined methods. Heating precursor near or over melting point of the matrix result in expansion due to the gas release from the decomposition forming agent, leading to a closed cell foam structure. The releasing of hydrogen gas from titanium hydride starts around 400 degrees, which is markedly below the melting point of most commercial aluminum alloys. This picture shows the production of metallic foam by powder metallurgy route. Aluminum powder, say we are producing aluminum powder, foaming agent, some reinforcing elements such as alumina. We are mixing them. Generally, we are using three-dimensional turbulent. And then compacting, and then get green dense materials. Since it contains lots of porosity and cracks, it is impossible to form them. That's why we are hot extruding that material to obtain a solid compact, and then rolling, and then forming in a special furnace, and then get the metallic foam. Sometimes we are using reinforcing element. In order to improve the stability of metallic foams, ceramic particles, mostly silica, alumina, or boron carbide are commonly added. These ceramic particles is believed to inhibit melt flow through increase the bulk viscosity, thereby decreasing the rate of cell coarsening and drainage of liquid throughout the cell structure. During forming process, these particles attach to the gas-liquid interface and modify its curvature, reduce the pressure difference between the plate border and the cell wall. These are aluminum foam produced by powder metallurgy route. When you look at from the outside, it looks like a normal aluminum, but when you cut it, cross-sectional area contain lots of porosity. It looks like a sponge. Because of this porous structure, it is very low density. It has very low density. That is important. This is the sample produced in our lab. The density was about 0.6 gram per centimeter cube. A sample can float into water easily. That's why this material is very important. When we will look at the mechanical properties of samples, this is tensile behavior of foam material and bulk material. Tensile properties of foam material is not good because of lots of porosity on the sample, which act as a notch effect. That's why reduce the tensile properties of the samples. But compressive strength of sample is quite good. That graph shows the bulk material compressive strength, that is metallic foam. Actually, the dark area is here is the amount of energy absorption of bulk material. That's the small area. This open gray, that big area is the amount of energy absorption of metallic foam. So we can say that compressive strength of these materials quite good. This picture shows the appearance of tubes with adhesively bonded aluminum foam interiors after axial compressive test. This is tube filled metallic foam. This is the empty tube. When we applied compressive test on these materials, the shape is like this. And then the graph shows that this is the empty tube. This is foam filled tube. So that's quite good compressive strength of the metallic foam. We can say that. That picture shows the compression test of tubes fit with aluminum foam insert. That is empty one. That is filled with metallic foam. That's with a little bit different composition. Actually, this picture shows the possible usage of the metallic foams for automotive frame. We can use metallic foam in some part of this frame. Actually, some leading car companies are working to support some parts of car with aluminum or magnesium foams. This is the side supporting block of Ferrari made of aluminum foam. Look at the right-hand side here. That's the aluminum foam supported somewhere here. It was in the conference of Italy. I've seen that this Ferrari is shown there. Actually, metallic foam for automotive industry, when we look at it, can be used in different applications. That is the steel gear wheels. The outside is stainless steel, inside some metallic foam. That is another example. That is automobile body sheet supported by metallic foam here. If you have a big machine frame, you have to support with metallic foam actually. That is about 6 meter length and very big machine frame. That's why it was supported with metallic foam. There's another example for usage of metallic foam. This is the shock absorbing of aluminum foam buffer for roadside guardrail. That's here. Metal foam for different application. I have to show you some tunnel covered with metallic foam here. That is church in Korea. The ceiling of the church had been covered with metallic foam. That's the Seoul Metro, contains some metallic foam. That is metallic foam for bridge construction in USA. That is another applications. That's the sandwich aluminum foam screw here. That is aluminum sandwich. That is 3D molded parts and also foam filled profile. Actually, the important thing is for metallic foam for powder metallurgy. Metallic foam can take the form of mold, whatever it is. Actually, this is the mold. This is the metallic foam, comes out like that. It doesn't matter whether it's a basic shape or some complicated parts. How can we produce? Actually, there are a number of production methods. This is production of metallic foam from small precursor materials. Actually, we don't use these precursors so much, but just to show how metallic foam comes out. This video is very good. Okay. When you heat it, the precursor formable material, it starts forming, and then sometimes you have to take it out. If you want to control the structure, if you want to control the mechanical properties, or you have to put some limiting plate in somewhere here. This is another things that the metal foam filled tubes, that is conventional forms produced in IFAM in Fraunhofer Institute in Bremen. Sandwich foam and other types of metallic foam. The outside is non-formable materials, inside is foams. Sandwich panel consisting of metal foam core and 2 metal face sheet can be easily obtained by bonding the face sheet to piece of foam with adhesive. Alternatively, formable raw materials can be roll-cladded with metals. It can be steel, aluminum, or titanium, or whatever it is, by attaching each side of the formable precursor before rolling. We are doing that one actually. The conventional non-formable layers need to have a significantly higher solidus temperature to avoid melting during forming expansion. Otherwise, the cover layer also melt. This is the production of sandwich foam. That's also a good video. In both sides of sandwich, non-formable metal. The inside core is formable materials. When you heat it up, formable materials start forming. Look at the outside is intact, so you can stop whenever you want. If you want, you can go a little bit more, and then you can get sandwich forms. Okay, both sides are non-formable materials. Inside is formable precursor material. Actually, spherical forms, now called advanced pore morphology, is new one. This process, recent development of Fraunhofer IFAM in Bremen, for this a large number of granules made of a formable precursor material. Generally, sheet materials are cut into rectangular shape, are continuously fed through a bed furnace to effect the forming. During forming, it takes spherical forms due to the surface tension of materials. Then the foam elements are coated with an adhesive and filled into a mold. Using a mild heat treatment, the adhesive is actuated and cured, and then finished foam parts can be removed from the mold. This picture shows sandwich structure, 3-layer. You can go further if you want, or you can keep it 1 or 2 layers. The other is 3-dimensional molar parts containing advanced pore morphology forms. How can we produce that one? That video shows very good. Okay. You are cutting rectangular shape formable precursor. Because of surface tension, it turns spherical shape. If you have a very big material, okay, the bottom side is a little bit flat, but nowadays we prepare special mold for this, just we can get very nice, very spherical samples. Okay, I will show some materials and experimental procedure about that materials. We work a lot actually, just I will give some information about that. We use aluminum powder and Aluminix 231 powders from ECA. Blowing agent, we use titanium hydride from Eldridge. Reinforcing elements, silicon carbide from Eldridge and boron carbide from Nurol, Turkey. Compaction was 600 megapascal. Preheat treatment 550. Deformation rate 50 to 70%. Forming temperature 690 to 710 centigrade. In order to produce very big metallic foam, we specially designed furnace, the mobile flow. So whenever we want, we take the sample out. And also this furnace contains some special propeller to get homogeneous distribution of the temperature inside the furnace. Experimental result. This actually some morphology of the Aluminix 231 foam at 690. Sample contain various amount of forming elements. That is 0.5% titanium hydride, 1%, 1.5%, and 2%. So 1% is a small porous structure, 0.5% small porous structure, 1% coarse and thin wall thickness. When you go further, density is decreasing, but the mechanical properties also decrease. This is pore morphology of LMX231 form at 710. Again, sample contain various amount of forming elements. That is 0.5% titanium hydride, that is 1%. After that, 1.5% and 2%, because of high temperature and high amount of forming elements, some collapsing happen, and we take these samples out, and this cannot be used. This is the electron microscope of self-wall of homogeneous wall thickness. Look at this one. They are very good wall thickness. This is again silicon carbide reinforced aluminum foam, cell of wall, distribution of reinforcing element in the cell wall. So it can be said that it is homogeneously distributed. When we look at the effect of forming agent on the linear expansion rate of aluminum-based foam at 710, linear expansion rate of pure aluminum is just over 400%. But LMX231 goes almost 400 when they contain 0.5 and 1% titanium hydride and then start decreasing. This is the density of aluminum foam. This is pure aluminum, that is LMX231. They show similar trend. Firstly, it is about 0.8 gram per centimeter cube with 0.5 titanium hydride. When you increase the titanium hydride or reinforcing elements amount, it starts decreasing. When you go 1.5% titanium hydride, it came to 0.4, and then because of the collapsing of the sample, again, density rised. This is the pore structure of aluminum foam at 710, 0.5, 1, 1.5, and 2% reinforcing element. When we compare these materials with the LMX231, pore structure is not good, but 0.5 and 1% is reasonable, but after that, it's coarsening of the pore. That's why mechanical properties also not good. This is appearance of spherical advanced pore morphology aluminum foam, depending on the amount of reinforcing element added at 690. That is 0 without reinforcing element, 1%, 2, 4, and 8. After 8%, it doesn't get a proper spherical form. The pore morphology of these samples also not good, so we kept our experiment after 8. This is the cross-sectional area of the sample contain various amount of silicon carbide particles. This is 0, this is 1%, 4%, and 8%. After 8%, the structure is not good. Just in order to show you, I kept it this one. This is the linear expansion rate of aluminum foam. That's the 0% goes to 500%. When we add 1% silicon carbide, it is just over 300%, 2% over 400%, and 4 and 8 about 450%. And then because of the collapsing, it start decreasing. This is the density of aluminum foam, depend on silicon carbide addition. That's the 0%. 1%, the density is 0.6. 2, 4, and 8% about 0.5, and then start increasing. This is the aluminum foam sample produced in various forms. Actually, we produce lots of samples. These samples also produced in our labs. That's the conventional samples, sample profiles, and tubes filled with aluminum foam. This is the sandwich structure. This also cross-sectional area of the sandwich structure. That's quite good, actually. This is very big sample, 250, and the thickness is 15 millimeters size, aluminum foil. This is for armor plate. Aluminum foam reinforced armor plates, I would like to mention. Boron carbide reinforced aluminum-based metallic foam was produced and then used in sandwich structure of polymer-based armor plate in order to reduce the shock effect during explosion. This research was the desire of Turkish Armed Forces. All ballistic tests were performed by them according to the relevant NATO STANAG standards. We are allowed to provide only a limited test result. This project was carried out by GAZİ University. At that time I was working there. İzmir Institute of Technology and Barış Electric, we work together. Aluminum foam supporter armor material against blast effect, actually. This is the polymer-based armor plate normally used in some armored vehicles. Now we add some aluminum foam inside here. And then blast test was carried out on this sample. This is the blast test setup according to NATO STANAG standards. This is our plates. This is TNT, 6, 8, and 10 kilograms TNT were used for this test according to the STANAG test. Okay, just I will show a fifth test for you. Look at it. This is the 10 kilogram TNT. And then this group is 8 kilograms TNT. This is a little bit low. Now I want to show slow motion blast test of the sample. Several cameras in somewhere and then taking the picture and the videos during this test. Okay. Oh, sorry. Front and back side of armor plates before and after ballistic test. That is before test, front and back side of our armor plates. This is after test. They are intact actually, no problem occurred here. I couldn't give some detailed information about that because I am not allowed. Just in order to show the energy absorption capacity of aluminum foam, last video taken from the Fraunhofer Institute while I was working there. This is normal metal. This is the metallic foam. Look at.
Die Stahlkugel zunächst auf die Stahlplatte fallen.
Okay. This is metallic foam, keeping very, very nice. Okay. As a conclusion, aluminum and Alumex 231 powders were formed with various amount of forming agent at 690 and 710 centigrade degree, and spherical forms with the addition of silicon carbide and boron carbide particles were formed at 690 degree, and the test results are given below. The amount of forming agent was found to be one of the important parameters for forming, particularly for pore structure, linear expansion rate, and morphology of both pure aluminum and Alumex-231 foams. 1% titanium hydrate was found to be the most suitable amount of foaming agent for foaming of both materials. For all conditions, foam produced from Alumex-231 powder exhibited more homogeneous pore structure compared to sample produced from pure aluminum powders. With high amount of foaming agent, result in a thinner cell wall, together with partial agglomeration of pores and finally collapsing of foams. During the production of spherical foams, reinforced freeze sample exhibited highest amount of linear expansion and lowest density. On the spherical foam containing silicon carbide, the best result was obtained on the sample containing 4% silicon carbide particles. This sample exhibited more spherical structure, together with lower density, homogeneous pore structure and higher linear expansion. Sample contained more than 8%. Silicon carbide did not have a spherical shape, encountered with the difficulty of forming an homogeneous pore structure. This was attributed to the high amount of reinforcing element, which increased the viscosity of the melt. I would like to thank TÜBİTAK for supporting this work. And also, I would like to thank the Frono for Ifan Bremen for providing some pictures and videos. Thanks for your attention. If you have any question, I'll be very happy to answer that one.
Thank you very much, dear professor. It was really interesting topic. Produce a foam structure by using these techniques. Yeah, maybe some audience may ask a question about that.
Yeah, they are welcome.
Mansour, dear Mansour, we are listening
to you. So much. I would first like to thank Professor for the wonderful presentation. I just wanted to ask about the potential development of refractory metal foams, such as tungsten or molybdenum. What do you think about this?
Actually, they can be done, but that's very difficult because of the high melting point. That is difficult. Nowadays, they are producing some, say, up to copper or nickel or iron, but it can be done. But nowadays, the foaming agent for that material is difficult. That's why nowadays it is impossible, but later on it could be.
I understand. Thank you so much for your answer. Thank you.
Thank you, sir.
Yes, Hakan.
May I ask a question to my PhD supervisor? Firstly, I would like to thank you to attend this conference, and every time you support us. My question is about the new challenge of this area, especially for materials, not only one material, but also what is the way of these studies?
Actually, Hakan, you know that recently intensive studies on light alloys are continuing. As far as I know, Audi is covered at the bottom of the car with aluminum foam. BMW and Mercedes are working to that one. I am sure that in near future, in many areas, that you will see metallic foam in some areas.
Similarly, we can connect to defense industry because they are especially car or automobile fabric. Your examples. It can be connect defense industry, Professor.
Yes, as I showed in our videos, we covered the bottom of our cars for explosion in order to get the shock effect. Actually, we get very good result. I am sure that it will be used soon for defense industry.
Thank you very much, Professor.
As well, is there any question?
Mr. Gökhan, may
Yes,
I ask a question?
Please, please.
My question will be related with this presentation. I wonder the possibility of the magnesium alloys. Can we apply this kind of foam processing into the magnesium alloys? Have you any experience with the subject? Thank
Actually, we haven't done magnesium, but magnesium is very easy. It can be done very easily. Magnesium, aluminum, or even titanium can be done. But if the sample with a high melting point, that is difficult because you cannot find material for expand those high temperature materials. But magnesium is easy.
All right. Thank you.
We haven't done actually, but it is easy.
All right.
Now we are trying to produce gold.
Oh.
Yeah.
Oh, fantastic.
We started copper, but we are going to gold.
Okay. Gold.
Yes, yes.
It's gonna be very high in the price.
Actually, some companies are supporting us. Some gold companies are supporting us. Hopefully, in a near future, we will start that one.
Thank you very much, sir.
Welcome.
Yes. Is there another question to dear professor? As far as we understand, most of researchers wonder that the process for now is only restricted only aluminum base material.
Not aluminum nowadays, even stainless steel, nickel,
right?
yeah, they can be produced. But now we are working aluminum because that's easy.
You're just only working on aluminum
yes,
alloys.
We are working aluminum. And
pure aluminum or aluminum alloys?
Aluminum and aluminum alloys together.
Can be done. Okay, yeah. Very nice. And dear professor, may I ask a question? I wonder that actually, could you arrange the density of the this structure after processing? Could you control the density amount of the structure after processing, or there is a ratio for this? Can you do this easily?
Yes, you can control. Actually, it depends on the temperature. It depends on the forming elements. It depends on the time. If you take your sample out very early, you can get the small size porosity with a high density. If you go a little bit further, you can get very large size with a high amount, low density. So you can control easily. There are a few parameters such as forming temperature, alloying element, forming duration, reinforcing element, and by controlling those parameters, you can control the structure.
Very nice. Okay, very good presentation. Do you have any question? Sorry.
If you want good mechanical properties, keep it small pores with thick wall thickness. If you want to reduce weight, a little bit big pores and thin wall thickness, you can keep it.
According to applying parameters. Okay, very nice. Is there any question after these? I think, dear Professor Hakan, shall we finalize the part of the section? What do you think?
Actually, I like these sessions, not only this, but also all 4 sessions were perfect. I joined all and I like them. Because of this, I don't want to go to home. I wanna continue. We met, but everybody have to go their home and
nobody wants to go home. How come? If you go home, you have to cook.
Yes. Thank you very much, Professor. Thank you very much, Gökhan Küçüktür, our session chair. Thank you very much, all participants. Now you can close, Gökhan Hocam.
Thank you, Gökhan. Nice to see you.
Nice to see you. Thank you very much. I would like to thank you also for all speakers and audience as well. And tomorrow, our symposium will be going on with interesting topics. We will see what will happen.
We'll see.
Thank you.
Okay.
Thank you very much for
Bye.
everything.
Thank you.
Okay.
Thank you.
Bye. Bye.
Good night.
Good night.